Alrighty, we're going to wrap up our talk about probability here today with looking at what they call compound events. So, meaning we're doing more than one thing. So, not just like simple probability like we were dealing with in the previous lesson when we were looking at just one selection or one thing. Compound means there's more than one thing happening. And if you think back to your English when you talk about compound sentences, it's phrases or things that are connected with words like and or or. So, we're really going to focus in on those compound words, the and and the or, to help us figure out what's going on here. So I'm going to separate the top and bottom here. The two on the top I think you're familiar with. We've already dealt with independent versus dependent. If you're making separate, distinct choices, so you're choosing something and then you're choosing something else, they fall into two categories. Either they're independent, which means the choice doesn't affect. So that first choice does not affect your future choices. So it does not affect future choices or selections that you make. And then there's the idea of in or dependent, where the choice that you make first does affect your future choices. So I think it's a situation that we've talked about already, but it's really important to keep in mind now when we talk about multiple events, multiple choices. So I'm going to choose and I'm going to choose again. I need to know if what I'm choosing affects how many things I'm choosing from, what's left, in other words, after I make that choice. The thing that we haven't talked about yet is the difference between mutually exclusive versus mutually inclusive. So I want to talk about the difference here. So when we talk about things that are mutually exclusive, think about the word exclusive. If something's exclusive, what kind of words pop into your head? Well, or like the exclusive resort. What would that mean? Well, it's very elite, right? It's separate from where everybody else is going to be. There's something special about it. So when we think about that mathematically in probability, exclusive means it's very separate. The choice is separate. So there's no overlap happening. They're distinct, separate choices that we make. So the choices that we're choosing between are separate. So it's something where we're doing very distinct options, either this or it's that. So when you're connecting and thinking of the words that we're talking about, we're going to be dealing with the word or in terms of compound sentences here, because it would be either this or that. So let me give you an example of that. Exclusive would be if you're choosing between let's say you want to have a dinner option and you want to choose between chicken or steak. You are going to have both. It's not like there's some combination animal that's both a cow and chicken, right? It's either chicken or it's steak. That would be mutually exclusive. So you're looking at two separate things. Or in sports, say you're looking at all the kids that play girls basketball and then all the kids that play boys basketball. Two separate rosters, two distinct choices that you're making. Mutually inclusive, if you think of the word inclusive, if we include people or the people are inclusive, that means they can maybe, they're part of it, right? There's parts that are together. So when I think of inclusive mathematically, we think of that being some sort of an overlap. The choices are not separate. There are people or selections that maybe could fall into more than one category. Let me give you an example with the sports one. So say you take all of the kids that play basketball and then all the kids who play lacrosse, and you're going to look at the total number of kids that play basketball or lacrosse. Are there kids maybe that play both basketball and lacrosse? Well, sure, there probably are, which means if I count them in the basketball roster and I count them in the lacrosse roster, I have now overcounted them because I counted them twice. I don't need to count them twice. We're always looking for counting and how many ways can I do something. That would be too many ways. So we have to deal with that overlap. So inclusive versus exclusive is really looking at, is there overlap between your categories when you're choosing or not? When we talk about independent versus dependent, these are compound again, but these are and situations. I want this to happen and that to happen. So then we're looking at a little bit different scenario. Does my choice affect what's happening in the future, that second selection, or doesn't it? So we have and or. Those are compound words, and those are our compound events that we're going to look at. So the way I wanted to do this is look at one example and walk through the 4 different representations so we can talk about what that looks like. So we're going to talk about independent, dependent first, then inclusive, exclusive, so we can talk about what that looks like. So let's start with independent events. So 2 independent events. And look at how they wrote the rule. They said the probability of A and B. All that means is event A and event B. So I want to see what's the probability that both of them happen. And notice the connecting operation. You take the probability of the first event times the probability of the second event. This is an and situation. I want both of these things to occur. This is the counting principle, this and this. So if I want all the ways one thing occurs and all the ways another thing occurs, we find the product. That's the shortcut for doing the list. So when you do it with probability, it's the same thing. It's a multiplication. It's the number of ways each thing can happen. How can they happen together? And this and this. So when you take a look at the example, let's see if we can figure out why this and situation is independent. So we have the same bag of candy for all these first four examples. Find the probability of selecting a mint, replacing it, and selecting a cinnamon. I'm going to have you focus in on a couple different key things here. All right, so the box part, let's talk about that first. Replacing it. What does that tell me? These are independent events. So what I do first is not going to affect what happens after it because I put the candy back. I replaced it, so that's independent. What does the word and tell me? I want both of these things to occur. That means it's going to be a product. I want probability of something and something else. I want both to happen. That's multiplication. If you can think about how you say it, the word and means you're going to find the product of those two. So the probability of selecting a mint and the probability of selecting a cinnamon on your second draw. Now I know it's and, so that's going to be multiplication. So because it's independent, when I look at how many are mints, that would be 3 out of 10. I put it back, and this is the important thing, because that means when I'm selecting my cinnamon, there's still 10 options in the bag. So I put it back in, that's why it's independent. And for cinnamon, I think there's only one of them. So the probability that both of those things happen is that product, which would be 3 out of 100, or a 3% chance. It's not very likely that that would happen. But the idea is it's independent, so I have the same number to select. So I still have 10 in the bag once I do my original selection. Okay, so how is it different when I look at it for dependent? This is kind of interesting. So let's look at the difference in how they wrote it. It's still the probability of A and B. It's still a product because it's an and. I want both of these things to happen. That's my compound word. But it says probability of A. Okay, that was the same. Now it's how they write the second one. The probability of B following A. That looks kind of weird, but what that means is you did A first, and that choice that you made affects what your choices are for B. So when they say B following A, that means because you did A first, there is something that changed. It is dependent on what you did first. So instead of just saying probability of B, which would stand alone, no, you did something first, and now that affected what I have left. So let's take a look at the example. It says if you select 2 candies without looking, find the probability that both are caramels. Or another way to say that is you get a caramel on the first one and then you get a caramel on the second one. Notice the connecting word, and, right? You get a caramel and another caramel. So this is definitely an and. It's not so clear or so obvious to people, though, why this is dependent. So in any part of that question or that statement, did they say they put the first caramel back? Not at all. So if they didn't say it, you have to assume they didn't do it. It would have been a lot better if they would have said, select a candy, do not replace it, and then select another candy. But if they just say they took 2 candies out, it means they didn't put it back. You have to assume that that's what that means. So this is definitely a dependent. It would be super helpful if they actually said, yep, that would be a situation where I didn't put it back, but they didn't. So we have to assume that they didn't, though, because they didn't say that they did. So we want the probability of drawing out a caramel. So I'll say the first caramel, and then the probability of drawing out the second caramel. And I'm going to talk about this as an and because it's one and the other. It's not an or, it's an and. I want both things to happen. So what's the probability that I select that first caramel out of there? Well, it looks like there are 4 caramels out of the 10 total, but now I didn't put it back. So if I want a second caramel, there are only 3 left, and there's only 9 left in the bag. So it changed my outcome. It's dependent. Now, it wouldn't have had to be a caramel then a caramel. What if I would have said a caramel and then a mint without putting it back? Well, the first fraction would have been the same. Caramel still would have been 4 out of 10. But if it would have been mint next, it would have been 3 out of 9. I guess that would have been the same thing, right? Because there's 2 mints, so kind of a bad example. Let's do the cinnamon next. So what if it would have been a caramel and a cinnamon? So 4 out of 10. Cinnamon then would have been 1 out of 9. So it only affected really the denominator when you look at what you have left. So pay attention to what you're choosing. But this is definitely an and. I want both of them to happen, but it's dependent because I did not put that value or that candy back in the bag. So that would be 12 out of 90, which I think reduces down to, let's see, if I divide them each by 3, that would be 4 out of 30, so 2/15. Double check and make sure that's okay. Now, I know some of you might have done this differently, or we talked about it yesterday in a little bit different way. I want you to compare what we just did to 4 choose 2 over 10 choose 2. And I want you to do that ratio and see what you come up with for that. 4 choose 2, 6 ways. 10 choose 2, 45 ways, which also reduces down to 2/15. So combinations, order didn't matter, they're just both caramels. I had 4 caramels to choose from and I chose 2 of them, not choose. And then 10 candies total, I chose 2 of them. Doing a combination is the same thing as saying I am selecting dependent events, one after the other, where my choice affects my future choices. So for those of you that are very hung up in, like, I always like to do fractions and that's the way I like it, that's fine, but sometimes combinations in that situation can be easier. What if there's 100 pieces of candy in there and you're going to choose 50 of them? I wouldn't want to do 50 different fractions to represent that, with the denominator going down by 1 for each one of them. So it makes sense to think of it as a combination in that scenario because it's a time saver. So combinations mean the same thing as dependent situations. So the choice you make does affect the future ones. So you can think of it either way. Okay, so let's switch gears now and let's talk about the difference between exclusive versus inclusive. So mutually exclusive events. So this means it's a single event. So there's one thing happening. And in exclusive, it means the two choices that you have are separate from one another. There's no overlap. And notice the probability of both things happening, we have now the sum in between. It's a plus because this is an or. I'm making one selection and I want either this or that. That would be success. So either this outcome or that outcome. And there can be multiple. This is only for 2 different things, but you could choose a whole bunch of different ways to win whatever success is. And it would be a sum for all of them. So let's look for the keywords. It says find the probability of selecting a chocolate or a mint. So notice you're only making one selection, right? It's not like independent dependent. You're only choosing once, and you're choosing between a chocolate or a mint. Both of those would be successful. So the probability of getting a chocolate would be success. The probability of getting a mint would be a success. So either of those. So you think of, if you're comparing with either or, this is always going to be a sum situation. And I bet a lot of you would have done it this way anyway. How many are chocolates? Well, there are 2 of them. How many are mints? Well, there's 3 of them. So together, there would be 5 out of 10 ways, or a half, that I would be successful. That would be the outcome I'm looking for, chocolate or mint. It's just like the example we did when we talked about the marbles that could be yellow or red. Well, how many ways can you win? All the yellows, all the reds together, right? You kind of sort of unconsciously just add them together, but we would get both of those options. So it would be 5 out of 10 or a half. But these are exclusive events. Why is it exclusive? Well, when you look at these 2 different kinds of candy, there's chocolates and there's mints. There's nothing that's like a minty chocolate. They're not in both categories, right? There are chocolate candies and there are mint candies. There's none where they're both chocolate and mint together. So it's exclusive, so I don't have to worry about any overlap. Okay, so how does that compare with this? My goodness, look at the rule. So mutually inclusive events. It looks really complicated. We got a lot of stuff, but let's look for what's similar. The first part of the rule is the same. It's a sum. This is an or. So it's the probability of the first or the probability of the second. But here's this extra part now. We subtract off what I would call the overlap, the things that are in both groups. So they're either A and B. So let me go back to my example I did before. So if you are a basketball player and a lacrosse player, you would have been counted in the basketball rosters and the lacrosse rosters, and now you've been overcounted. We need to subtract off the overlap. So things that are inclusive means your choices belong to more than one group. All right, so let's take a look. Find the probability of selecting a chocolate or a chewy candy. All right, chocolate or chewy. So the probability of getting a chocolate, probability of getting something that's chewy, or, so this is plus, why is it going to be inclusive. Let's take a look. So chocolate and chewy, are there some that are both? Well, there's 2 chewy chocolates, right? And there are 4 chewy caramels. So we have a whole bunch that are chewy, but notice 2 of those chewy ones happen to be chocolate as well, which means if we count them in the chocolate category and we count them in the chewy category, you have just overcounted. So we have to subtract off the overlap, which ones are chocolate and chewy. So the ones that fit in both of those categories. So that's what inclusive means. We have overlap because there are candies that belong in more than one category. So the ones that are chocolate, there are 2. The ones that are chewy altogether looks like there'd be 6. And we subtract off the ones that are both chewy and chocolate, which just happens to be 2. In this case, it happens to be the same number. It wouldn't have to be. So 3/5 of the time, we'd be doing this. That would be the likelihood that this would happen. So it's an or, so that means it's one selection, this or this. So it's adding, but inclusive this time because we have overlap. So look for your connecting word. Would you say it with an and, which means independent, dependent, you're timesing, or would you say it with an or, which would mean adding, and then it's inclusive or exclusive. So we're going to look at some unique scenarios. So we're going to look at 6 different examples now where we're going to talk through some of the different things that can happen. So here we'll start with a deck of cards because of course we have to do that in probability. It says to find the probability of selecting a red, replacing it, and then selecting a red face card. Okay, so how many selections are you making, first of all? Well, you're making more than one. So this is an independent or dependent situation. And which one is it? Well, look at your key phrase here. Replacing it means it's independent. You have the same number of cards on your second choice as you do on the first one. And then I'm going to circle another word here. And so you got a red card and then you want a red face card. You made 2 selections, independence, 2 separate probabilities. That means we're going to be multiplying. So the probability of red and the probability of a red face card. You want both of these things to occur. It's not a this or this, it's a this and this. I want both to happen. So what's the probability of getting a red? Well, 2 of your suits are red, so half the cards in your deck are red, right? So I'll start with this, but really that's just a half. And then red face. So what are face cards? Jack, Queen, King. And then if it's red and it's a face card, that means it would be only from diamonds and hearts, so that would be a total of 6 out of 52. So we've got a half times 6 out of 52, and that looks like that would be 3 out of 52 would be the total number of ways I can do this. So it's independent because you replace the card, and it's an and. I want both of them to happen, so that's a multiplication situation. All right, let's take a look at the next one. Got a whole bunch of different types of balls in a box. Okay, it says determine whether the events are independent or dependent first. So read through it. Circle which one you think it is. All right, now, does it say anywhere that they put the ball back before they chose the second one? Doesn't anywhere. So I have to make the assumption then that this is a dependent situation. So the first choice affects the number that I have left to choose from. Now, the way we say this then, 2 balls are chosen. You chose, let's see, probability that both are tennis. So that means on the first draw, I got a tennis ball. And then on the second draw, I got a tennis ball again. Did you notice the connecting word that I said? So the first draw, I got a tennis ball. And then on the second draw, I got a tennis ball. And, right? Multiplication. I want this and this. Even though it's still independent, it's still an and scenario. You want both of those things to happen. You're drawing twice. I want this to happen and that to happen. All right, so what's the probability that you get a tennis ball on the first one? Well, that would be 9 out of, I think there's 24 in there total. And then the second tennis ball, well, you didn't put it back, right? We have to assume that they didn't because they didn't say they did. That means there'd only be 8 tennis balls left and only 23 total balls left in that box altogether. So it's going to be fewer in both situations, which would be 3 over 23. Now, if I change this, what if I said you'd get a tennis ball first and then a racquetball? Well, that wouldn't affect your first fraction, right? It would still be 9/24. But then a racquetball, there's 5 of them. So it'd be 5 over 23. Again, I still didn't replace it, so that denominator would still go down by 1. So it's an and. You want both to happen, so multiply. But it's dependent. The choice I made affects future choices. Okay, let's take a look at another one. Kind of a just a completely ridiculous example, but it has to do with a game show. So kind of like The Price is Right or something like that. Grew up with Bob Barker, making your different selections. So this is a game show where you just select a card. So you pick a card out of a deck, and then depending on what the card says, that determines your prize, whether you get a prize. So the cards, two of them have cars on it, 5 of them have a major appliance on it, 10 of them have trash cans, and 13 that say loser. So what would you consider to be a winning situation in this? Well, I would say getting a car would be a winner. Getting a major appliance would be a winner. Getting a picture of a trash can, not sure that that's necessarily a winner, especially if they don't actually give you the trash can. There could be some discussion on that. Loser for sure is not a winner. So I think really only cars and major appliances would be considered to be winning situations. How many cards does this contestant get to pick? Just one, right? You draw one card out of this. So this is not an independent-dependent situation because you're only making one choice. But it's a compound situation because there are multiple ways that you could be a winner. How can you be a winner? Well, you can be a winner by getting either a card or a major appliance, right? So if you think about what your options are, there's more than one way to win. Cars or major appliances. Notice the word I used. You wouldn't say a car and a major appliance. You don't get to win both things, right? You only get one thing. You get either a car or a major appliance if you win. They're not both. So it's definitely an or situation, which means we're going to be adding those probabilities. So the probability to win would be if you get a car card or a major appliance. Now here's a question for you. Is there any overlap between those two probabilities? In other words, do I have to subtract anything off? Is this exclusive or is it inclusive? Well, unless your refrigerator, for example, has wheels on it and you can drive it, there's no overlap here. Either you're a car or you're a major appliance. So they really are separate. I would say that these are exclusive, unless we do some crazy stuff to our appliances or whatever. Or if your car also refrigerates things and washes your clothes and something else like that. So they are definitely different. So we have 2 out of 30 different ways to win with the car card. We have 5 out of 30 ways to win with the major appliance. So that would give us 7 out of 30 ways total, which I think most people just sort of automatically do. Okay, how many different ways can I win? 2 are cars, you have 5 appliances, 7, right? But this is or because you have more than one way to win. It's either this or it's that. You wouldn't say and, right? Because you don't get both. You only get to choose one. Okay, just like when you go to a restaurant and you're going to order food and you would say, like I said, chicken or beef. You don't get both. You either get the chicken or you get the beef. If you say chicken and beef, that's a whole different scenario. Then you are actually getting both. But this is definitely or, car or major appliance. Okay, now the next one, they calculated some things for you already. They did the probabilities already, but it's to get at the idea of inclusive versus exclusive. So in this particular classroom, they were surveying kids about their hobbies, like what they were interested in doing. And so they surveyed them and they found out that 5/8 of the students collected baseball cards. Now let's just be clear that 5/8 could be reduced. It doesn't mean that there's 8 kids in the classroom and 5 of them said baseball cards. So that could be a reduced number. So 5/8 of them said they collected baseball cards. Comic books was 5/12. So again, it doesn't mean there's 12 kids in the class and 5 said comic books. That could be reduced. But 5/12 of the class said they collected comic books. Now, just with that information alone, if we stopped there, what you'd have to consider then when you think about your groups, there's some kids that collect baseball cards or there are some kids that collect comic books. Is it possible that there are some kids that would collect both baseball cards and comic books? Well, sure, and that's what they say then. The probability that a class member collects both is the third. What is the probability that if you just choose one kid out of the class, just at random, that they collect either baseball cards or comic books? Huge connecting word here, or. That means I get the outcome I want or win success if I have students that collect baseball card or if they collect comic books. So when I talk about or, that means I have subtraction going on. So it's one or the other. You're only selecting one kid. So it's one selection, this or that to be winner. Now, here's the thing. Is this inclusive or exclusive? Well, we've got some overlap, right? Collects both. So this means there's some overlap, inclusive, between those different categories that we're talking about. So if we just did all the kids that did baseball cards, which is 5/8, oops, that was a plus, sorry. Ooh, plus, 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 or, right? Plus all the kids that collect comic books, which was 5/12. If we just stopped there, we'd be missing the fact that, oh, there's a whole bunch of kids that collect both. I need to subtract off the overlap. So I need to subtract off the kids that collect baseball cards and comic books because we would have counted them twice. So I'm going to subtract off the third of those kids in the class that collect both. So I think we end up with 17/24. So it's being able to understand the difference between is there overlap or isn't there. Okay, last one I want to do, and I know it's not on your note sheet originally, but if you can kind of jot down the important information here, or kind of copy this down, I want to talk about a question that's very similar to the things we've done the last couple of days, but I'm adding in a phrase here that's critically different. It says at least 3 girls are chosen. So you have this class, there's 6 kids. And again, I'm using small class size numbers because it's easier for you to do the calculations. In an art class, there's 4 girls and 2 boys. 4 of the children are chosen at random to act as greeters for an art exhibit. So that means they just get to stand by the door, whatever, greet people as they come in. Does the order that they are chosen matter? Well, there's nothing special about the roles they get to play, so they're just all greeters. So no, if I give a list of the 4 kids who are greeting, it doesn't matter the order I write them in, they're still all going to get to be greeters. So what's the probability that, notice what I circled, at least 3 girls are chosen? All right, now, what would winning be in this situation? If I talk about 3 girls being chosen, what would be a winner or outcome that could make this true? Well, if there's 4 people total, if I want at least 3 girls, that means I could do 3 girls and 1 boy. That would meet the requirement. Or I could have all 4 be girls, right? So I could have either 3 girls and 1 boy, or, notice the connecting word, or all 4 girls. There's more than one way to be successful. When you see the word at least, that means there's multiple outcomes that would meet the requirement that we're looking for. So 3 girls and 1 boy, or 4 girls. Now, inclusive or exclusive? Well, this would definitely be exclusive. When you're choosing from the class rosters, you're on the girl list or the boy list, whatever, so you've got that. So we have those rosters, so it's separate. So it's exclusive. There's no overlap here, but there's definitely multiple ways that you can make that selection. So 3 girls, 1 boy, or 4 girls. All right, so let's talk about what we would do before to select 3 girls and 1 boy. Well, how many girls are there to choose from? 4. We already talked about that this order doesn't matter, that we pick them. So combinations, and you're choosing 3. How many boys are there to choose from? 2, and you're choosing 1. Now, notice I didn't put an operation in between, because I want you to think about it based off what we just talked about today. I want 3 girls and 1 boy. Multiplication, right? Counting principle. So think about the words that you would say. That really helps. And then in the denominator, total number of ways you could do this. Well, 6, choose 4, right? We're choosing 4 kids. All right, 4 girls. Well, I'm going to choose from my girls. There's 4 girls to choose from, and I've got to choose 4. All right, well, think about that for a second. How many ways can you choose 4 people from a group of 4? 1, right? Choose all of them. If you type in 4, choose 4 in your calculator, it's going to say 1. Now, I want to show you what some people would say for the second part. 2, choose 0. What would that mean, 2, choose 0? Well, 2 boys and you're choosing none of them. Try typing that into your calculator, see what it says. 2, choose 0. And if you do that, interestingly enough, it says 1, because how many ways are there to choose no people from a group of 2? Well, 1 way. Don't choose anybody, right? I know a lot of people wouldn't even put that, but really what you're doing is I am 4 girls, no guys, right? So that's what it means if I choose 4 girls. And then again, it's 6, choose 4 on the bottom. So when we put that together, I think that's 8/15, and then we have 1/15, which gives us 9/15, or 3/5, I think is what that ended up to be if I'm remembering my numbers correctly. So this idea of overlap or not, independent, dependent, is critical when we're looking at counting. So think of how you would say it. Is this and or is it or? Really helps to decide if you're multiplying or if you are adding.